Welcome everybody to Algebra 1, Section 1.1, the first lesson of the course. We're talking about the real number system and properties today. So the name the real number system, the word real kind of implies that are there numbers that aren't real or imaginary? That's kind of weird, and believe it or not, actually that's exactly what it implies, and that's real, or it's correct that there are imaginary or non-real numbers. And before you start panicking and wondering how we're going to deal with that, just know that we aren't going to deal with that. We aren't going to do anything with that. During Algebra 1, it'll be an Algebra 2 issue. So for now, any number we talk about during this course of Algebra 1 will just be a real number. Now, we're going to have all these different number groups or subsets we're talking about here, as you can see. And all these different ones we're going to need a way to identify them from one another quickly rather than having to write them out all the time. Otherwise, that would just kind of get become too much for us. And so it'll make our life a lot easier if we take care of that. And so, for example, the real number system will be a capital R, R for real. And we're going to kind of leave this blank for now, just knowing that any number we're going to use in this course are real numbers. Now, every number that is real is either considered to be irrational or rational. So all of these groups here are part of the rational number group. And irrational numbers, let's talk about those first, are decimals that never end, and I'm going to change this here, don't repeat. They never end and they don't repeat. And so it says think mumbo jumbo numbers. That's less about how big they are, but rather how long they are. So to use the irrational number shortcut, it'll be a capital I. So just like R for real, it's I for irrational. And so pi is the most famous irrational number. Pi famously never ends or repeats. People talk about how many digits of pi they can memorize. There's songs going about listing digits of pi. Other irrational numbers would be like the square root of 2. Square root of a number just means what times itself gets you that number. So there's no number where you can multiply it by itself and get 2. So we say there is no square root of 2 or no defined square root of 2. And so we just say that it's irrational because it'll never end or repeat. If you try and do the square root of 2 on a calculator, eventually your calculator just runs out of space on the screen and it stops listing numbers. That's not because it ends, but rather it just had to stop somewhere. So another example would be the negative square root of 101. 101, similarly to 2, no number times itself is 101. And whether or not it's negative or positive has no impact. So negative numbers, positive numbers are both able to be irrational. And another one would be like the pattern 1.010010001 ... Obviously, there's a pattern we see there that it's adding an extra 0 every time before another 1. And even though there's a pattern, it doesn't actually repeat. No numbers repeat. It doesn't go just like 0, 1, 0, 1, 0, 1, or 1, 1, 1, 1, 1 forever. It continues to change, and even though it's predictable, it's still changing. And that's what we're concerned about there. So all of those would be considered irrational numbers. So now talking about rational numbers here. Rational numbers would be, well, we can't use R since we already used R for real, so we're going to use Q, okay? And that comes back to other languages that math was done in for centuries and centuries and centuries before English was even a thing. And so Q ended up becoming used. So all fractions and decimals that end, or I'm going to scratch out this have a repeated pattern, but rather or repeat. So fractions as well as decimals that end or repeat are rational. So some examples of these would be the fraction 1/3, or the decimal negative 0.67. Once again, whether it's positive or negative has no impact here on whether it's irrational or rational or real or at all. And so because the decimal ends, it is rational. We could also do 1.1 repeating. That's a decimal that repeats. It's 1.11111 forever and ever and ever, all through eternity. And so because it repeats the same number, it is rational. And another example would be like the square root of 16. So even though it's another square root like we saw over here, what's different about the square root of 16 compared to those previous square roots is that 4 times 4 is 16. And so because 4 times 4 is 16, the square root of 16, you could just replace this with like a 4 here, and all of a sudden, that's a decimal that ends, believe it or not, because it's secretly like 4.0, but we just don't write the 0.0. So because of that, the square root of 16 is rational because it's actually just 4. And so I'll also just put the number 2 there to also make sure that we note that this is a number that ends. Integers. Integers are a subset of rational numbers. So as we get lower and lower and lower down here, we're getting more and more specific, okay? So every rational number is real, but not every real number is rational. For example, all of these are real numbers, but not rational, okay? So integers, we can't use I since we've already used that with irrational, so we'll use the letter Z. And all of these are capital letters, by the way. It's very important that they're all capitalized because lowercase letters are reserved for use for variables in math. So capital Z. And so these are going to be positive numbers as well as negative numbers, so positive and negatives. They're also going to be non-decimals and non-fractions. All of these are true for integers. And so you could do like dot, 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 -2, -1, 0, 1, and 2, dot, dot, dot. All of those are integers. So all of these numbers smaller than -2, such as -3, -4, -5, so on and so forth. And all these numbers bigger than 2, such as 3, 4, 5, so on and so forth into eternity, both directions, are integers. We don't care whether it's positive or negative or 0, which is neither. We know as long as there are no decimals and no fractions. And once again, all integers are rational, but not all rational numbers are integers, such as these first 3 rational numbers listed earlier are not integers. The next group we have are whole numbers. We'll use that capital W because we haven't used W yet. And these are going to be non-negative integers. Non-negative integers. And I'm going to use INTS to abbreviate integers because honestly I'm lazy and I don't want to write it all the way out. It's a good practice to be able to abbreviate things in your notes. That way you don't have to write it out every single time. It can speed up your process, make it more efficient, can help to not clutter up your paper as well. And so non-negative integers, or I'm just abbreviating as INTS for integers. So the non-negative ones would be 0, 1, 2, 3, dot, 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 forever and ever and ever. So it doesn't continue forever to the left because we don't get into negatives. And the last group of numbers that we're going to talk about today are the natural numbers. Natural, we'll just use the capital N there for natural. And these are going to be the counting numbers. So think any number that you would normally count with in a typical setting. Now, typically, we don't count with the number 0. You don't start counting off people in a class or people in a line by going 0, 1, 2, 3. Instead, you just start with 1. And so it'd be 1, 2, 3, dot, 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 forever and ever and ever would be the natural numbers. They're also the numbers that we see in nature. I think you don't normally see negative amounts of things in nature. Like you don't see -3 cows when you're driving. You also don't see like 2.5 rabbits typically in a yard. If there is a half rabbit, that means obviously something altered that rabbit and made it a half rabbit. And like I mentioned earlier, every number in one of these sets over here is part of the groups above it. So every natural number, such as 1, 2, or 3, is also whole, an integer, it's rational, and it's real. It's all of the above groups, okay? But every whole number is not automatically natural, or every integer is not automatically whole. Similar to how every square is a rectangle, but not every rectangle is a square. Or how every freshman at PHS is a high school student, but not every high school student at PHS is a freshman. There's, sophomores and juniors and seniors. Now here we're going to be putting this to use by naming all the sets of numbers to which each number belongs. And these are where these letters are going to come in, those capital letters we're using for each set. That way we don't have to write out the entire set. And so the number 30, for example, on number 1. 30 is a counting number. It's not negative, it's not a decimal, it's not a fraction, and so it's a natural number. So natural number is the smallest set to which it belongs. However, we're supposed to name all sets to which it belongs. And because it is natural, it's automatically all of these groups above it. And so we also have to list whole, integer, rational, and real. Now, as you continue going through these problems here for numbers 2 through 12, I encourage you to pause the video, try as many problems as you can or want to or have time for before continuing the video. That way you can try it out and then compare what you did to how I did. So that way you get that first attempt to learn. It's going to be very helpful for you to be able to learn it better, okay? So number 2, negative 11. Negative 11 is not a natural number or a whole number, but instead it comes in when we talk about integers, because those are positives and negatives, where these are just the negatives. But it's not a decimal, so it still counts as an integer. Same with it not being a fraction. So we got Z for integer, Q for also being rational, if it's part of the integers, and then since it's part of rational and integers, it's also a real number. Number 3, 5 and 4/7. Well, this fraction here, 4/7, tells us all we need to know. Fractions are rational numbers because they cannot be integers, whole numbers, or natural numbers. And since it's rational, it's also real. Square root of 21. Well, like we were talking about earlier with the square roots of 2, negative square root of 101, and square root of 16, we were saying it all comes down to whether or not it's a perfect square. And so for square root of 16, we said 4 times 4 is 16. So the square root of 16 is 4, meaning it's rational or even just a natural number. Whereas 2 and 101, neither of those are perfect squares. No number times itself is 2, and no number times itself is 101. So it ends up becoming these decimals that don't repeat or end. And the same thing is true for the square root of 21. No number times itself is 21. So this is an irrational number as well as being real. Because remember, whether it's irrational or rational, they're both real numbers. Turning our attention to number 5. On number 5, we have the number 0. 0 is not a number we count with, but it is non-negative. It's a non-negative integer, not a decimal nor a fraction. So it is a whole number W, as well as Z for integer, Q for rational, and R for real. Because remember, every group belongs to the groups above it as well. So then moving on to number 6, negative square root of 9. So as we were talking about the square roots, it comes down to whether it's a perfect square or not. 9 is a perfect square, 3 times 3. And so when we say negative square root of 9, it's really like negative 3. And negative 3 is not whole nor natural, however, it is an integer. So we have Z for integer, as well as Q for rational, and R for real. Now, if we talk about number 7, it's a fraction, which might make us think instantly it's rational. However, we have to be careful here. This one's tricky. 6 divided by 3 can reduce. 6 divided by 3 is 2. So it's actually the number 2, which is one of our natural numbers. You can count with it, or you would normally count with it, I should say. You could technically count with any number, but you just don't normally count with a lot of numbers. So it's natural, N, as well as all the groups above it. So W for whole, Z for integer, Q for rational, and R for real. On to number 8. On number 8, we have pi. As we talked about earlier, pi is the most famous irrational number. It never ends nor repeats. So it is I for irrational and R for real. Number 9, 5.3 repeating. So we have that repeating bar tells us it's going to be 0.33333 forever and ever and ever. So that makes it a rational number, even though it doesn't end, because it does repeat, it's rational, as well as being real. Square root of 144 over negative 3. So we see that square root, and we see it's a fraction. Okay, we got to, let's take it one piece at a time though. Square root of 144. Is 144 a perfect square? Is there a number that multiplied by itself will get us 144? And 12, in fact, does the trick. 12 times 12 is 144. So we change it to 12 over negative 3. And now we say, okay, well, 12 over negative 3, what would that be? Well, 12 divided by negative 3 is negative 4. So it's actually just a normal integer. So what looked like it might be another group actually belongs to the integer. So it's an integer, it is rational, and it is real. So we got Z, Q, and R. Number 11, negative 2.875. That is a negative decimal. So more importantly, it's a decimal, which automatically tells us it's one of these two groups. And because it's a decimal that ends, it's rational. So it's Q for rational as well as R for real. And then last but not least, number 12, square root of 17 over the square root of 17. Well, anything divided by itself, except for 0, which we'll get into later, but anything divided by itself otherwise is 1. So square root of 17 divided by square root of 17 is 1. So even though 17 is not a perfect square, because nothing times itself is 17, and so you would think that might mean it's irrational. However, because it's something divided by itself that's not 0, we just have it equaling 1. So that is a natural number. So we have N, W, Z, Q, and R. So now notice as we look back on these 12 that all 12 of them are real numbers, because as we talked about earlier, every single number we will encounter this year in Algebra 1 is a real number. So now continuing to work on these organization of the real number system, we're supposed to place the letter of each value. So when you're placing the value for 7, you can just put the letter A instead of writing 7 in whichever one of these groups that it belongs, or the smallest group it belongs to. So 7, for example, is rational. So you could put it here technically, but we're not just trying to put it in anywhere it fits. We're trying to put it in the smallest place it fits. So more specifically than being rational, 7 is a natural number. So we would put A there, because even though 7 could go here, here, and here, most specifically it is natural. Now I do want to note here that I'm going to put the letters for the different number groups. So we have N for natural, W for whole, Z for integer. I almost put I. I made a mistake there. I is irrational. And then Q for rational, and then these are all part of the real number system. So I'm just going to say everything in this box is rational, whether it's in the big circle everything in this box is real. My apologies, I misspoke. Whether it's this big circle for rational or the small circle or small oval for irrational. I encourage you once again to go ahead and go through here and see if you can place as many of them as possible in the correct groups. This once again the smallest group, and be careful, just like we did in the last problem set, you'll have to simplify some of them before continuing. So letter B, is negative 36 over 12. 36 divided by 12 is just negative 3. So that is an integer, so we're going to put that for letter B. And I realize here my Z for integers is pretty sloppy, so I'm going to erase that and rewrite that to make it a little bit nicer, less sloppy now. And so now I've done A, I've done B, now I'm on to C. So C is negative square root of 36. So we see square root, so we got to decide, is 36 a perfect square? Well, 6 times 6 is 36, so this is really just negative 6. So, like negative 3, that is an integer. Letter D is pi. Pi is irrational. It never ends nor repeats. E is 6.48. That's a decimal that ends, so it is rational Q. F. Well, F is negative 2. Negative 2 is not a decimal, not a fraction, but it is negative, so it belongs with integers. Up next is G, negative square root of 10. Just like we talked about with C, negative square root of 36, we have to decide, is 10 a perfect square or not? and it is not a perfect square. Nothing times itself is the square root of 10. So that means it is irrational. G. I also just realized that earlier, instead of writing D for pi, I just wrote pi, which is fine. It wouldn't be wrong if you did that. I just want to be consistent in writing the letters in here and not confuse anybody. So if you were confused by that earlier, I apologize. Next up is H, which is the number 0. 0 is a whole number. It is the only number that is whole but not natural. I comes up next, and I, 2 1/6. It's a fraction that can't be reduced, so that would go with rational. Next up, we have J. J is negative 0.7 repeating. A decimal that repeats is rational. And last but not least, K, the square root of 4 over 81. Well, would any number times itself be 4 over 81? Kind of a weird question, but let's break it down to just the top and the bottom. Would something times itself be 2? Sure, that'd be, or something times itself be 4 rather, I should say, and that would be 2. And would something times itself be 81? Sure, so 9. So if you did 2 over 9 times 2 over 9, that would indeed be 2 times 2, which is 4, and 9 times 9, which is 81. So that means 2 over 9 is the square root of 4 over 81. 2 over 9 is a fraction that does not reduce further, meaning K would be rational. And that now finishes up this problem. So now we're on to this problem set here, which once again I would encourage you to pause the video and then work on these problems and then continue the video after you've started them. Number 1, which expression does not name an integer? So A is in fact an integer. It's a negative non-decimal non-fraction. C is an integer. It's a non-decimal non-fraction. D is a fraction, but it reduces to 2, meaning B is our last fraction, and it only reduces to 3 over 7. It reduces by 2 on the top and bottom. So B would be our answer. That is not an integer. Number 2, which expression represents an irrational number? A decimal that does not end or repeat. So A repeats. B is a fraction. D is a number minus itself, so that would just equal 0. So sure, the square root of 3 is irrational, but 0 is perfectly rational. And then square root of 75. 75 is not a perfect square, meaning it will not ever end nor repeat. So B is our answer. Next up, we got number 3. Which number is not a whole number? Remember, whole numbers are our counting numbers. I instantly see a negative, and so I know that must be the answer. But let's check out the others just in case. 8, yep, that's a counting number. 0, oh, my apologies, I said counting numbers. Counting numbers are natural numbers. I might have confused some people there. But whole numbers are the non-negatives, non-fractions, non-decimals, so the non-negative integers. So 0 is non-negative, and 18 over 3, while being a fraction, reduces to 6. So B, negative 10, would be a negative number, meaning it's an integer, but not a whole number. Next up is number 4. Which of the following is a true statement? Negative 9 is a whole number. Well, wait a second. We just said whole numbers are non-negative. So that automatically tells us that one is false, so it can't be A. B, square root of 25 is an irrational number. That would be true if 25 is not a perfect square. However, 25 is a perfect square. The square root of 25, oh, my screen just changed over there. The square root of 25 is 5. So that one cannot be the case. Wait, sorry, is a true statement. Not the case. Again, actually irrational. I thought I read it wrong. Turns out I read it correctly. Letter C, 0 is a natural number. Natural numbers, remember, are the counting numbers. We do not count with 0, so that is false, meaning it has to be D by process of elimination, but let's check it out just in case. 2/3 is a rational number. Yes, it is a fraction, and fractions are rational numbers, so it is letter D. That is true. Which of the following statements is false for number 5? So we're looking for a false statement this time. All real numbers are rational. That's not true. There are some real numbers that are irrational. So A is false, so we can cross that one out. B, every integer is rational. So we look at integers, and they are all part of the rational. So that's true. Let's try out letters C and D just in case, though. Oh, it says is false. My goodness gracious. I keep messing this up. So A was our false one. We said that one was not true. My apologies for messing that up. B was false. Well, let's look at C and D anyway. C, all natural numbers are integers. So look at this. Natural, part of integer. That is true, but we're looking for the false statement. So because that's true, we can cross that out. D, every whole number is real. Yes, all the numbers we'll talk about this year are real, including those whole numbers. So yes, A was the only one that's false. All real numbers are not rational. There are some that are irrational. Moving on to number 6. Give an example of a number that is not a whole number, that is a whole number but not a natural number. When we talked earlier, the only whole number that is not natural is 0, because whole numbers are the non-negatives, not the non-negative integers, and 0 is neither negative nor positive, where the natural numbers are the counting numbers, aka only the positive ones. Number 7, give an example of a real number that is not rational. So any real number that is irrational, so irrational numbers, that could be any number that doesn't end or repeat. So pi could be an example. Otherwise, the square roots of imperfect squares, such as the square root of 17 or square root of 2 like we had earlier, or that pattern that doesn't repeat, but keeps changing, that we had earlier, like the 1.010010001, where it continues to add a 0. And number 8, give an example of a rational number that is not an integer. So to be an integer, it cannot be a decimal, nor can it be a fraction. So rational number that is not an integer, just pick any decimal that ends or repeats, or any fraction. So you do the decimal 2/3. Let me fix that 2. You could also do, once again, any decimal that ends or repeats. So the fraction 2/3 would be an example. Moving on, we're going to talk about properties. Properties are statements that are true for any numbers. They justify steps when simplifying expressions and solving equations. So they're basically one of the backbones of math that allow us to do a lot of things that we end up doing. So some properties that you hopefully are familiar with at some point along with your math. You've seen these, even if you haven't seen them in a while or you're not used to calling them what they are. So the first is the commutative property, and this is true for both addition and multiplication. And the main idea, and not very dense math words, but rather in words that hopefully make more sense to you, is that the order of values doesn't matter. The order of the values doesn't matter when we add or subtract. So it still matters for subtraction and division. I think I said add or subtract. I meant add or multiply. So some examples would be just with variables. A plus B is the same thing as B plus A. Or another example could be 2 plus 3 is the same thing as 3 plus 2. Both of those are 5. And so for multiplication, you could do x times y would be the same thing as y times x. And you could also say that 2 times 4 is the same thing as 4 times 2. Both scenarios would give you 8. The associative property, which is also true for both addition and multiplication, tells us that the grouping of numbers doesn't matter either. Now, once again, it still will matter for subtraction and division, but not for addition and multiplication. Now, grouping refers to us using parentheses or other grouping symbols. So grouping symbols are like the parentheses, brackets, absolute value, things like that. So, for example, if we had 3 numbers A, B, and C, if A and B were in parentheses, meaning you add those first and then C last, it'd be the same thing as if B and C were in parentheses. So whether we add the first 2 first or the last 2 first, it doesn't matter. So an example of this could be saying that if you add 5 plus 1 first and then add 3, it'd be the same thing as if you add 1 plus 3 first and then you add 5. Just to showcase that would be 6 plus 3 compared to 5 plus 4. And both of those would get you 9. And this is also true for multiplication. So if we did a times b times c, it'd be, and a and the b were in parentheses, meaning do those first, and a times b times c were b and c in parentheses, so you do those first. Either way, the result's the same. So for some numbers, we could have 2 times 4 in parentheses, meaning to do those first, and multiply by 7 after. And if we have 4 times 7 in parentheses, so you do those first and multiply by 2 after, we get the same results. So let's show that. 2 times 4 would be 8, and 4 times 7 would be 28. And both scenarios, 8 times 7 and 2 times 28, give you 56. The identity property. This is also true for addition and multiplication. Basically, the main idea is that what you start with stays the same when you're done with it. Now, what works for the identity property as far as what causes it to stay the same, sorry about that, what causes it to stay the same for addition and multiplication differ. So for addition, adding any number by 0 keeps it the same. So 5 plus 0 is 5, 8 plus 0 is 8. For multiplication, multiplying by 0 does not keep it the same. Rather, multiplying by 1 will keep it the same. So 1,000 times 1 is 1,000, for example. Next, the inverse property of addition or multiplication. The idea is you're using the opposites, okay? So you're using the opposite. Now, opposite can mean a couple different things depending on what we're doing in math. Now, also, I don't like the word cancel. I don't think it's very mathematically accurate for most of the ways that we use the word cancel. So I really try not to use that word. So instead, we're going to call it undo. We're going to use the opposite to undo a value. And what's going to happen is we're going to take it back to the identity. The additive identity was 0, adding 0 kept it the same. The multiplicative identity was 1, multiplying by 1 keeps it the same. So when you do the additive inverse, or the inverse for adding, you get it back to 0. When you do the multiplicative inverse, the inverse for multiplying, you get it back to 1. And we'll see this here. So a plus its opposite would be negative a. It's just a different sign, but the same term would give you 0. So for example, you could also do 5 plus a negative 5 is 0. Once again, different sign, but same number. Whereas with multiplication, if we were to have a times 1 over a, that would give you 1. And the reason why that would work is you would have a over 1, and this would end up being, if we take a detour down here, would give you a over a as you multiply straight across, a times 1 and a times 1, which results in 1, because it's something divided by itself that's not 0. You could also show actual numbers with this, so you could do like 5 times 1 over 5 would be the opposite of it, the reciprocal, or the flipped version. So 5 is secretly over 1, so you do 1 over 5 for the reciprocal. And that would give you 5 over 5, which would give you 1. You could also cross-reduce, or some people call that reducing early, where we say 5 and 5, 5 goes into 5 once, and 5 goes into 5 once. And now we have 1 times 1 on the top, giving you 1, and 1 times 1 on the bottom, which we could put over 1, or you can just call it 1. The property of 0, this is only for multiplying. So far everything that we've talked about for these properties are true for both addition and multiplication. However, this is only for multiplying. And it states that multiplying by 0 always equals, not sure why that moved again, sorry about that, but multiplying by 0 always equals 0. So a times 0 is 0. 17 times 0 is 0. 1/2 times 0 is, times 0 is 0. 1 over a times 0 is 0. If I make this a negative 1 over a, it's still 0. Anything times 0 is 0. The distributive property is the last property that you're probably familiar with, and the distributive property is just repeated multiplication. So the idea is that you multiply one value or a value to an expression inside parentheses, and rather than write parentheses out, we can just show parentheses there. If you want to write it out, it would look like this. I like to think of it as it looks like parent he, and sis. I'll try and spell it. So to showcase this, if you were to have a times a quantity, or quantity just means things inside of a parentheses, a times a quantity of b plus c, or the sum of b and c, and you distribute the a, you'd have a times b and a times c. A times b would be ab, and a times c would be ac. Not to confuse with the thing that cools you down in the summer, AC. You could also do 2 times the quantity of x plus 7, or the sum of x and 7. And that would be 2 times x, which is 2x, and 2 times 7, which is 14. Now I do want to showcase another example here, to showcase that if we had... actually, I want to showcase something else first, rather. My apologies. That if I were to change this plus 7 to be a minus 7, that change that would happen here is this would then become a negative 14, because you would have a positive 2 times a negative 7. So you can think of this as a minus 7 or a plus a negative 7, and either way is accurate. So we can think of that minus as being associated with the 7 there. So if we were to make that change, that's what would be affected. Now if I were to give another one here, such as negative 5 times the quantity of y minus z, now as we do negative 5 times y, we get negative 5y, and negative 5 times this negative z, remember we can take this minus and just associate it with a number or term behind it. So negative times a negative is a positive, and that'd be 5z. More properties, these are going to be our newer properties here today, would be the reflexive property, symmetric property, and transitive property, and closure property. So the reflexive property, the main idea is that a value always equals itself. So anything is equal to itself. So for example, 16 equals 16. That's true. Kind of seems overly simple, right? 5x equals 5x, something equals itself. Or 4y squared equals 4y squared. The symmetric property, symmetry just means it looks the same on both sides of something. So a lot of times we think of mirrors when we think of symmetry. So if A equals B, then B equals A. We can flip it around. So for example, if, rewrite my if x equals 3, then 3 equals x. We can switch which side of the equal sign things are on, so that 3 can go on the left or the right, and the x can go on the left or the right. And we really don't care as long as what's on those sides, as far as what makes up each side stays the same, even if they flip sides. So if all of a sudden one of these changed to a 5, well, that's an issue. But as long as they remain the same in both scenarios, we don't really care which way it's written. Another example could be if 5x equals 30, then 30 equals 5x. Another new property we're talking about here is the transitive property. Okay, the prefix trans just means moving, so things transportation, things that move you from one place to another, such as cars, trains, planes. Now, the transitive property has the same idea of moving or change. So if A equals B, and, that's my and symbol, B equals C, so A equals B, B equals C, then it must be true that A equals C. So we're saying that B is equal to both A and C, so they must equal each other, A and C. So in some other terms, we could have if 4 plus 3 equals 7, that's true, 4 plus 3 is 7, okay, and 7 is equal to the square root of 49, which it is true that 7 times 7 is 49, then it must be true that 4 plus 3 is equal to the, I need to fix my equal sign, square root of 49. Because once again, 4 plus 3 is 7, and 7 is the same thing as the square root of 49. So it's almost like we cut out the middleman there and just push those together. Next is the closure property, okay? And this is the last property we're going to be talking about today. The closure property just means that a set or a group of numbers is closed under an operation, such as addition, subtraction, multiplication, division, if when you do the operation, you always get an element or number of that same set. So for example, if you were to multiply two positive numbers, would you always get a positive number? If yes, that is closed under multiplication. If not, it is not closed or open under multiplication. So if an element outside the set is produced, so a number not what we're talking about, then the operation is not closed, or the set is not closed under that operation. So we're going to say whether these things are true or false, and if they're false, we're going to give a counter example. That just means an example of when it's not true. So integers are closed under multiplication. So if that's true, that would mean that if you multiply the operation, any two integers, you'll always get an integer. So remember, integers can't be decimals, nor can they be fractions, but they can be positive and negatives. So that's like saying, if I do 5 times negative 3, I'm not going to get a fraction or decimal ever. So meaning if I don't start with a fraction or decimal and I multiply, I won't get to fraction or decimal. And that is true. As long as you do not start with a fraction or decimal, you will not get a fraction or decimal when you are multiplying. So we're going to say true. Next, natural numbers are closed under subtraction, meaning if you subtract any two natural numbers in any order, you'll only ever get a natural number. So remember, natural numbers are the counting numbers, or only the positives that are non-decimals and non-fractions. So for example, that'd be like saying 9 minus 5 is equal to 4. Well, that's true. However, 5 minus 9 is equal to negative 4. So we subtracted two natural numbers. We did 5 minus 9, but we did not get another natural number. We got a negative. So that means it's not closed. So that is false. And this could be our counterexample right there. Anytime you would subtract a small number minus a bigger number would be a counterexample on that one. Number 3, even numbers are closed under addition, meaning if you add any two even numbers, you'll only get another even number. So it starts out even, it will only ever stay even if we add them together. So let's just test it with two even numbers. So 2 plus 4, those are both even, you get 6. That stays even. Well, let's test it with another couple numbers. 8 plus 22, I picked another couple random even numbers. Well, that would end in 30. And as we continue to try more and more scenarios, you would notice that they'll always give you another even number, because it is true that anytime you add two evens, you'll only get an even. So that means it is closed under addition. Next, irrational numbers are closed under division. So if we divide two irrational numbers, we'll only ever get an irrational number. Now remember, irrational numbers are the numbers that never end nor repeat. So we're saying if we divide those, any two of those, we'll never, ever, ever get a decimal that ends or repeats, or a non-decimal or non-fraction. So let's try this out. So if I do pi divided by the square root of 2, which we said both of those, are numbers that never end nor repeat, that would give me another crazy number that would never end or repeat. So that would give me another irrational number. However, there is something that we could divide pi by that would result in a number that is rational. And you would have to divide it by pi. Pi divided by pi is 1, because any non-zero number divided by itself is 1. So that would be dividing two irrational numbers, granted the same number, but still two irrational numbers, and getting a number that is rational. So that is false. And a counterexample is that one there. Any two irrational numbers, or any irrational number divided by itself, would be a counterexample. And the fifth one, perfect squares are closed under subtraction, meaning if you subtract two perfect squares, you'll always get a perfect square. Now remember, perfect squares means that anything times itself will get you that number, or a number times itself will get you that number. So for example, 16 is a perfect square, 4 times 4. 9 is another perfect square, 3 times 3. So we're saying that if we subtract any two perfect squares, you'll only get a perfect square. So if we subtract these two, we get 7. And 7 is not a perfect square. No integer times itself is 7. You can't get 2 times 2 and get 7. You can't get 3 times 3 and get 7. And there's no whole number or natural number or integer between 2 and 3. So this is false. And that would be another counterexample. And most examples you could think of would be counterexamples on this one, as a matter of fact.